Welcome to the Crash Training Podcast. We're going to help you work to restore or preserve the highly perishable skill set of crash reconstruction. All right, everybody, and welcome to episode number 7 here on the Crash Training Podcast. I am your host, Bobby J. Mullinax with Crash Training Solutions, and in this episode, we're going to talk about what the F. All right, and that's just a little play on letters, I guess, and we're going to talk about drag factors in this episode. And this is going to kind of round out the look that we've been doing at the minimum speed equation by talking about one of the biggest variables in that equation, which is the drag factor. And it also is going to answer a question that we had come across that was, what is drag factor in relation to coefficient of friction? Are they the same? Can I use the words interchangeably? Was the gist of that question. So we're going to get into that, and it's going to be a good review, or you may be learning this for the first time, who knows? But we're going to talk about mu and drag factor in this episode. Now remember, if you're watching this on YouTube, it is still beneficial, but if you're listening to us on one of our audio formats, Apple Podcasts, Spotify, or any of those, go to crashtrainingsolutions.com/podcast, crashtrainingsolutions.com/podcast, and you'll be able to download all the visuals from this episode as well as all the other episodes as well, and that just gives you a nice visual reference that you can look back at later. So that's definitely something you want to check out. Before we get started or after we get started, doesn't matter, but just make sure you go and grab those visuals. It's going to be helpful down the road if you ever want to review some of this stuff. So let's look at drag factor versus mu. Now, mu is represented with this weird looking lowercase, almost cursive looking U symbol. All right, and that is the Greek symbol for mu, and it is commonly used to denote the coefficient of friction of a surface. All right, in our case, usually we're talking about the roadway, but it could be other things. But for this example, we're going to look at a car skidding on the road like we have in the other episodes leading up to this. Now, what coefficient of friction is telling us is it is letting us know that this surface is completely level. All right, there's no grade whatsoever with this surface. It is a completely level surface, and when we have a completely level surface, we will call it a coefficient of friction. Now, when we have the drag factor, or the lowercase f, that is what we are referring to as a surface. When we are taking the friction value of the surface, and we are also accounting for grade or super elevation. So we could have an uphill grade, we could have a negative or a downhill grade, we could have a positive super elevation or a downhill super elevation, and that drag factor is taking into account the added force on that vehicle for going uphill, or the reduced force for that vehicle going, downhill or downgrade. So if that doesn't make a lot of sense, let's look at it this way right quick. So let's say that we have a car. All right, and we're going to say that our car is going to be skidding on a completely level surface. All right, here's my rectangle and 2 circles, which means that's a car right there. So we're going to look at it, and we're going to say that he is completely skidding on a completely level surface. All right. So there's no grade, there's no super elevation whatsoever. So we are dealing with mu in this case. And for this example, we're going to assign it a 0.71. So this is the friction for the roadway on a completely level surface. And if we have our center of mass here, we've basically just got the normal force of the vehicle. We don't have any added or decreased force by any kind of an angled relationship with the roadway, and that's going to make more sense here in just a second. So we're just on a completely level surface, and if I had this car and he locked up and he was sliding, to move that car on a completely level surface with a mu of 0.71, then it would take approximately 2,982 pounds of force for that vehicle to move forward. All right, so the way you can think about this is, even if you're from the private side, especially if you're one of our law enforcement listeners, I am willing to bet that everybody listening on this podcast at some point in time has had to push a vehicle. Whether it was stalled or somebody ran out of gas or whatever the case is, you have had to push a vehicle. And is it going to be harder or easier to push a vehicle on level ground or to push a vehicle uphill? Obviously, it's going to be harder to push that vehicle uphill because we have the force of the vehicle, normal force of the vehicle that we're having to overcome, but we also have this added force due to the angle that uphill or that upgrade has created. So let's say that in this case, we have a grade that is positive or uphill, and it is a 0.06. All right, now in this case, it would take, to push the same vehicle, and we're going to say that the weight of this car is 4,200 pounds. All right, I'm going to stick with 4,200 pounds. And it only takes 2,982 pounds of force to push that vehicle or get that vehicle to move on level ground. The same 4,200 pound vehicle, not at level, but going up a 6% grade, it is going to take 3,234 pounds of force to push this vehicle up this grade, because it's harder to push a vehicle uphill than it is downhill. All right, and the same thing, if we had the same vehicle and now instead of pushing it uphill, we're going to push it downhill. And now we're going to say that our grade is a negative or a downhill 5% or 0.05. We still have this angled relationship, but now it is getting easier for that vehicle to move downhill because it's easier to push a stalled vehicle downhill than it is uphill. And it's easier to push a stalled vehicle downhill than it is on flat level ground. So in this case, to push that vehicle, or to get that vehicle to move, I only have to have about 2,772 pounds of force to get the vehicle to move in that direction. So the question becomes, if I have a coefficient of friction and it's on a flat level ground, how do I know what the drag factor is at 6%? And how do I know what the drag factor is at downhill 5%? And if I want to adjust this, I can adjust this mathematically, but one of the easiest ways to do this is just kind of envision a set of a ladder or a set of stairs. And for every point above level that you're going to climb one rung of the ladder and you're going to add 0.01 to your drag factor. So if I'm at a 6% upgrade, I would just say 1, 2, 3, 4, 5, 6. And each one of these rungs represents 0.01 grade. All right, and I start out at a 0.71 on flat level ground, and then as I move up, I'm at a 0.72, a 0.73, a 0.74, a 0.75, a 0.76, and eventually I climb up 6 rungs of that ladder, and I will have a 0.77 drag factor. At a 6% incline. All right, so we've just basically pictured this as a ladder, and we've just started here at the middle of the ladder, and we've just climbed up 6 rungs, and we wind up at a 0.77. All right, the same concept we can do mathematically also. Some people love to have a formula for everything, and if you want a formula, you just say that F is equal to U or mu plus grade, and we would treat that grade as a positive or negative number. So I'm going to say that F is equal to 0.71 plus 0.06. So my F would be a 0.77. Same thing, now I've just did it mathematically instead of doing the ladder method. Now if I had a vehicle that was skidding Downhill at a negative 5%, I wanted to know what the drag factor would be for it. I would do the same thing. I would just work my way down. I would say 1, 2, 3, 4, 5. Again, every one of these little notches on my ladder represents 0.01 of grade, and now I'm just going downhill as opposed to uphill. So I would say 0.70, 0.69, 0.68, 0.67, and then finally we would be down here at a 0.66 at a downhill 5% grade. And again, if I wanted to, I could still work this out mathematically. I could say that F is equal to mu plus grade. So F is equal to 0.71 plus a negative 5%. And when I try to add a negative number, because I'm going to treat the grade in this case as positive and negative numbers, if it's going uphill or downhill. And when I say 0.71 plus negative 0.05, I'm going to still wind up at a 0.66. All right. Two different ways to do it. Neither way is wrong. It's just whichever way that you can understand it and explain it, then that's the correct method for you. So now we know what our drag factors would be. We would be at a 0.77 here, and we would be at a 0.66 here. All right, so also when we calculate that drag factor, and you notice that, let's say that we have a 0.76. All right, you notice that this is technically a unitless calculation. But a lot of times people throw this G on here, which kind of represents gravity. So we know in our drag factor equation, if we say force, or drag factor is equal to force in pounds divided by weight in pounds, once we divide the pounds, those cancel out, so we are left with a unitless number. That's why a lot of times you'll see people denote it as 0.76 G, because what this number actually is in this case 0.76 equals 76% of 1 G, which is 32.2 feet per second squared, or 9.8 meters per second squared. So when we slide that car and we come up with a 0.76, we're saying that this vehicle can get 76% of 1 G. Right, and that's why if we want to calculate our acceleration, we would say that acceleration is equal to our F factor times gravity. So we would say that A is equal to 0.76 times 32.2. And we would say that our A value in this case would be 24.47 feet per second squared. Because we have the percentage of gravity, and then we multiply it by our number for gravity, and that's going to tell us how much, how much downforce you're almost getting on the vehicle, how quickly it is slowing, what G-force the driver is experiencing. Because even at a 0.76, everybody has been in their vehicle and they've been driving down the road and they've had somebody slam on the brakes in front of them and in front of you, and you've had to get on the brakes pretty quickly. And when you get on those brakes quickly and you kind of feel that force pull you down, it's not much force. It's not like you're taking off in a rocket ship or something, but you are experiencing a 0.76 G in this case as you slow that vehicle down. So that's kind of why you almost feel like that little sink in your stomach sometimes or things like that. It's because of the gravitational force that you're pulling during that acceleration or deceleration. So that's why we multiply that by gravity to get our acceleration. All right, so the last thing we'll look at is how much of a difference does this number make if we're off a little bit. All right, so let's take this example. We're going to say that we've got a vehicle, and we're going to say that our vehicle comes in and he slides all the way to a stop. And at the end of this skid, he is going 0 miles per hour. And we're going to stick with that same 0.76 drag factor. And we're going to say that his distance that he travels is 75 feet. All right, we know from episode 3 or 4 that if I have a vehicle that slides to a stop over one surface, I can simply say speed is equal to the square root of 30 times distance times drag factor. So speed is equal to 30 times 75 times 0.76. I multiply everything straight across. I'm going to be with 1710 under the radical. I take the square root of that, and I'm at a speed of 41.35 miles per hour. But do I have a little bit of uncertainty in some of these variables? Yes, I do. I'm pretty sure that the drag factor is 0.76 because I tested it with an accelerometer, or I, maybe used a drag sled or something like that. But whatever method I use to figure out what the drag factor is, I'm pretty confident in it. But yes, it could be a little bit different. So it doesn't hurt to just do a quick sensitivity analysis. All right, we're pretty sure the vehicle is going 41 miles an hour. But if we're off a little bit, how much of a difference does it make? So for this time, to do that, to see how sensitive this drag factor is to this speed down here at the bottom of 41 miles per hour, let me just do the same calculation and drop the drag factor a little bit to see if it makes too much of a difference. All right, and so let's say we come down 5 points. And now we're going to say that, we feel pretty good that it's a 0.76, but, hey, maybe it's as low as a 0.71. All right, and if it is as low as a 0.71, what effect does that make on our overall speed estimate? So I'm going to run the same calculation twice, but this time I'm just going to plug in that 0.71 instead of the 0.76 that I came up with. So I say 30 times 75 feet times 0.71 for my drag factor. I'm at 1597.5 under the radical. I take the square root of that, and I'm at 39.96 miles per hour. So in this case, my speeds are pretty much the same. We've got about a 2 mile per hour difference in 0.05 drag factor. So this problem is not very sensitive to what that one variable is, and it's a good idea to do stuff like this ahead of time, because then if you're ever questioned about it, hey, you've already done the calculation. You know that this scenario we're not very sensitive for that drag factor. It's only 0.05. A 0.05 difference only equals not quite 2 miles per hour worth of speed. All right, so even if we are a little bit low, it's not making that huge of a difference in the outcome. And of course, we could do that with the distance as well. We could vary that. We could do them with the distance and the drag factor. It's just the more variables you throw in there, the more stuff you got to keep up with, and it's a little easier a lot of times in those cases to throw it in Microsoft Excel or something like that and just change your variables up a little bit and see how sensitive the numbers is. Because now we can say, we're pretty sure the vehicle is going 41 miles per hour, but, hey, we feel really confident that it's going about 39 to 41 miles per hour. All right, and that sensitivity could go in the other direction too. We could have underestimated our drag factor, but as far as law enforcement is concerned, usually we're trying to do a pretty conservative speed estimate, so we really wouldn't go and start adding speed onto our vehicle, but we will look, especially in law enforcement, look at if I'm a little bit lower on the drag factor, does it make a big difference in speed? If I'm a little bit lower on the distance, does it make a big difference in speed? All right, and we could work that out as well if we wanted to, but I think all you guys get the idea. So that kind of wraps us up for the most part on minimum speed. We've looked at a single slide. We've looked at multiple surfaces and the combination formula. Now we've looked at the F factor, what the F, and see how sensitive it is, see what it actually represents, see why we have to adjust it for different grades, and we've looked at the difference between coefficient of friction and drag factor. In the next episode, we're going to look at the velocity formula, and we're going to see head-to-head how the velocity formula compares to minimum speed. And this is the combination formula. And I'm also going to show you one more formula that kind of deals with the minimum speed that is going to be a little easier to use than that entire combination speed formula. So you may have seen it before, you may never have seen it. It is a pretty good formula once you get the hang of it. So next week we're going to look at velocity and we're going to look at minimum speed. We're going to compare both of them because that was another question we had. Because their velocity formula is a kinematic equation of motion, how does that compare to minimum speed, which is derived from kinetic energy? So we'll look at those all in episode number 8, which will be dropping here in a couple of days. So, remember, go to crashtrainingsolutions.com/podcast and grab those visuals. crashtrainingsolutions.com/podcast. And until next time, stay safe, and I'll see y'all guys on the next one.